So, last week we talked about emissions and options, technical options for greenhouse gas emission reduction. This week we're going to put a price on that, see how much it costs to actually reduce emissions. I'm going to talk about estimates, but more about the sensitivity of these estimates to particular assumptions, to get you a feeling of where do these estimates come from and how credible are they. I'm going to talk about one relatively new chapter for me, and that's the feasibility of deep cuts in emissions, ones that are consistent with the Paris Agreement. A chapter that is new this year is the distribution of the costs of greenhouse gas emission reduction, who pays, and if time permits, I'm going to also talk about the claims that you can reduce emissions and make money at the same time. This is where we are in the sequence. This week it's cost. Next week we're actually going to revisit instruments for greenhouse gas emission reduction. It pressed itself twice. Let's start with estimates of the total and marginal costs of greenhouse gas emission reduction. The first thing to note is that it costs money to reduce greenhouse gas emissions. If it doesn't, or if there were no climate policy, then essentially you can do with your emissions what you want. You can dump them in the atmosphere to your liking. You can use the energy that you would want without further constraints. And now climate policy comes along and you put on a carbon tax, say, and all of a sudden your emissions are costly. So what used to be free is no longer. And that immediately implies that the costs of your actions, or that there's a cost to your climate policy. So that's the intuitive reason. You can also look at this as a mathematical problem. Essentially, without climate policy, there is one constraint less on the energy system or the agricultural system. You supply energy at the lowest possible cost, meeting certain constraints about reliability and air pollution and those sort of things. But now with climate policy you put an additional constraint on the energy supply, namely that CO2 emissions also need to fall or stay within certain boundaries, and whenever you put an additional constraint on a mathematical optimization problem, your costs go up necessarily, unless that constraint is innocent, it doesn't bite. So it shouldn't be at all surprising to find that there's a cost to greenhouse gas emission reduction. Now this table shows estimates of these costs, not in total, but at the margin for 12 different climate policies, I had to count, and 13 different models if I'm not wrong. If we move from left to right, climate policy becomes ever more stringent, yes, and move from top to bottom, we're just looking at alternative estimates of these costs. Now the numbers here are not particularly insightful, so let's just look at the same results graphically. So this is the same table, but now we're looking at the results in a perhaps slightly more appealing way. So the targets that I picked is the 550, the targets that are here in the middle. Now the first thing to notice is that there is wide disagreement between models. So some models say that you can meet this particular target if you impose a carbon tax of $1 per ton of CO2 in the year 2020, and other models say no, you have to impose a carbon tax of $20 per ton of carbon, and the carbon tax is of course equal to the marginal cost of emission reduction per mole. So there's a factor of 20 difference between models for what is the same climate policy. So there's quite a lot of uncertainty about this, and I'll get back to the reasons why models disagree in a couple of slides. The second question is shown in this graph here, and that is the question, what does climate policy cost? And the answer to that question is not a number, but the answer to that question really is, what do you mean by climate policy? And there's three variations in this graph. The first are three alternative targets. So if we aim for an atmospheric concentration in the year 2100 of 650 parts per million greenhouse gas equivalents, then it's pretty cheap. If we aim for 550, costs go up. If we aim for 450, then costs go up even more. And this sort of gets you to the Paris targets, more towards the 2 degrees target than to the 1.5 degrees target. 1.5, you actually need to work harder than this. And this is an obvious, I think, conclusion, obvious finding, that the more stringent your target, the higher the costs of meeting that target, right? The harder you need to work. So I don't think that this should surprise you at all. But the design of this policy also matters. In blue, we're looking at a scenario where we have a target in the year 2100, but it doesn't really matter whether we have higher temperatures or higher concentrations before the year 2100 or not. And we did an exercise like that in the seminar, I think 2 weeks ago, where the question was, hit the target at 3 degrees in the year 2300, or hit the target at every period leading up to the year 2300, and that actually required much more emission reduction. Here the answer is not how much more emissions should you reduce, but what is the additional cost. And what you see definitely for more stringent targets, that if you can approach the target from above or below, this is the text that you need to impose, around 125. But if you need to approach the target from below, that is, the target is not just for a century from now, but for every year between now and then, costs at the margin double, right? It just becomes much more difficult to meet this target, and therefore much more expensive. So the design of climate policy matters. There's a second design element here, and that is shown in the green bars. And again, you see that if instead of the red and the blue we have the green, costs go up quite considerably. In the red and the blue, the assumption is that every country in the world imposes a carbon tax, and actually every country in the world imposes the same carbon tax right from the start. And this is a somewhat older exercise. The start here is the year 2020. If instead you allow middle income countries to start a decade later than rich countries, and you allow poor countries to start 3 decades later than rich countries do, but you maintain the same target, and of course the implication is that the rich countries have to work much, much harder to reduce their emissions because the other ones are not working. And if that is the case, you're in the green scenario, and you see that costs more than double, right, at the margin. So the question, what would climate policy cost, is a nonsensical question. You need to be much more specific. What do we actually mean by meeting a target? Who is working? What is the exact target? And so on and so forth. And what you see is that the costs are quite sensitive to this. Now this is true at the margin. It's also true for the total cost. And here you see same study Same table of results, and instead of giving the costs in dollar per ton of carbon, I now give the cost measured in $1 trillion. And again, you see great difference. Some models say, well, actually, let's focus on this one. Some models say you can do this for $5 trillion or for $4 trillion even. And other models say, no, it's going to cost you $44 trillion. So a factor 11 difference between models. So still a great great spread in results between models. Now you may think that $4 trillion is a lot of money, and $44 trillion is even more. And of course it is a lot of money compared to your bank account, right? And it is even a lot of money for Vladimir Putin, allegedly the richest man on the planet. But actually it is not a lot of money. The total world product, total world income is around 80 trillion. But this, and then you think, well, 4 trillion or 44 trillion is actually a lot of money relative to GDP. But this is the discounted net present cost. So it's the total cost of climate policy over the century. So the relevant comparison is to total income, projected income over the century. And if you assume growth is 3% per year, the discount rate of 5% per year, then the net present value of income is $3,500 trillion. And you really need to compare the 44 to the 3,500. So we're talking about a fairly small investment. We're talking about a fairly small cost to meet this particular target. And the reason that it is so small, I talked about last week, that wind and solar are almost competitive, or maybe they are competitive with coal and gas electricity. We talked about transport, where you can sort of like see it on the horizon, that you could decarbonize at a low cost, and so on and so forth. It simply doesn't seem to be that big of a problem. There's another way of looking at this. If you look at total cost for the economy as a whole, and you look at the share of energy on a cost basis, then you're talking about 2% of our total expenditure is on energy. And that may seem like a number that strikes you as low, because energy costs are actually a bit higher for most people, 10-15%. But a lot of what you pay towards electricity and towards fuel is actually not so much for the electricity, but it's for the grid. And the grid doesn't disappear, right? Actually what you pay towards the coal and the gas that comes into your electricity is much lower than the 14 pence per kilowatt hour that you pay. And the same is true for the gasoline that you put in your car. You also pay for the tank station and the distribution and the refining and so on and so forth. And actually the fuel share is much lower. And that is of course what we need to replace. It's not that we're going to magically do away with an electricity grid, or magically do away with distributing liquid fuels, right? So on a cost basis, energy is around 2% of the world economy, and that then immediately implies that even if you were to double the price of energy, then that cannot have a large economic effect, because it is such a small fraction of the cost. But we are not talking about doubling the price of energy. We are talking about adding 5, 10, maybe 20% to the price of energy. So it cannot have a large effect on the economy. And that is true today. Of course, what we have seen is that energy is becoming less and less important in the economy, and renewables are coming ever cheaper. So it cannot have a large effect on the economy, and that is exactly what these models find. Now, why is there so much uncertainty, so much disagreement between models? And I phrase this here as what would lead you to more pessimistic results about greenhouse gas emission, or about the cost of greenhouse gas emission reduction. The first, and we talked about that last week as well, is just what can you do to reduce emissions? And one example is nuclear power. If you switch to nuclear, then you emit less CO2. But do you think, as a modeler, that this is a feasible option? Yes or no? Do you think that society will actually allow you to build more nuclear? Yes or no? And if the answer to that question is yes, we can build nuclear without problems, then your costs of greenhouse gas emission reduction are lower than if you assume no.
Is it like the safest way of producing energy, nuclear?
Safe in what sense?
Good for them, like it's not environmentally destructive.
Well, nuclear has a waste problem, right? Nuclear waste. There are technical solutions to solve the waste problem. No, and that is to first cover it in glass, because that keeps the radiation down, and then stick it in a geological reservoir somewhere deep underground. The problem with nuclear waste is that in many countries the public is so scared of this that rational discussion is just impossible. Germany is a good example of this. The US is another example. So there is an agreed solution for the nuclear waste in Germany, but that requires that you transport the nuclear waste, and people are so afraid of that that they block transport, and as a result a lot of nuclear waste is stored at the nuclear power plants themselves in very unsafe conditions. So because the public is so afraid, they actually stop a reasonable solution. So nuclear is not inherently dangerous anymore. Also the new design of the design of the newest nuclear power plants, these things cannot explode. It's just simply physically impossible for them to explode. So that's the first reason. Do you have these options for greenhouse gas emission reduction available, yes or no? And since we are talking about modeling this for the next century, of course we do not know what options will be available technically and what society will permit or not. And therefore reasonable people disagree about what options are available, right? And therefore model results differ. Second thing that people disagree about is what is the cost of wind. Now that may stray, and obviously this is important. If you assume that wind and solar are expensive, then greenhouse gas emission reduction is expensive. If you assume that wind and solar are cheap, then greenhouse gas emission reduction is cheap. You may think, like, why do people disagree with this, about this? Actually, a lot of these cost data are commercial secrets. So it's actually very difficult for academics to get a good grip on what is the actual cost of wind and solar. So we observe that partly, but not necessarily completely. One example is the auctions for permits to build wind power in the North Sea. And one of the latest, last year there was an auction of this, And there was this German company that promised to pay these things for 5 cents per kilowatt hour, build giant wind turbines in the North Sea and then deliver electricity for 5 cents, euro cents per kilowatt hour, and everybody was looking at them like, really? Can you do this? Right? Because the current cost of wind power is more like 15 or 20 cents, not 5 cents. And you can sort of like take this as given. Here is a company that promises to build these things for 5 cents per kilowatt hour, so let's take that as a cost. But then if you look at how these things are actually structured and what is going on in this auction, first it is an auction for building wind turbines in the year 2028. So this is not a cost today, this is what a company thinks it can do in 2028, right? The second thing is that they're bidding for licenses. And the license goes to the lowest bidder. So if this company bids 5 cents per kilowatt hour and therefore gets the license, it essentially has an option to build these things rather than that it actually promised to do so, and companies can leave these licenses, leave these permits without consequence for them. There's no downside. But the upside is if you have the license, then your competitor does not. So you can also interpret this as strategic bidding rather than a credible estimate of the cost of wind power, offshore wind power in the North Sea in 2028, right? So it is actually hard to get down to what is actually the cost of these things. And it's not just true for wind and solar, it's also true for nuclear, right? Nuclear, the cost is essentially Électricité de France in Europe. It's a very secretive company, very hard to actually get out what they're doing, let alone that you would know how much the Chinese are paying for nuclear, right? It's just...
What space, like, how do you discover how much space you need to, like, for example, if you want to power like all of Europe, how much space would you need to acquire if you want to build like solar panels or wind power? Like how much, like where would you put them?
That is relatively easy because you know how much kilowatt hours a solar panel delivers per square meter, right? So that is just the multiplication of these two things, right? The energy density of solar power is quite low, so you need quite a substantial area. And the question is, where do you put them, right? If you put them on roofs, then you actually don't need, you're using area that is not used for any other purpose. If you're putting them in fields, it's a different story, because then you're competing with grazing sheep and those sort of things. The question where to put them is a difficult one. Essentially, at the moment, they go where the subsidy is highest, rather than where the sun is strongest or where the grid connection is best. So what we've seen in Europe is a lot of deployment of solar panels in Northern Europe and very little in Southern Europe, which, if you know anything about how the sun shines in Europe, it doesn't make any physical sense whatsoever, but they're just following subsidies. The same is true for wind. Wind goes where the subsidies are largest. I used to work in Germany. We used to joke that the subsidies were so high that it would make sense to build a wind turbine indoors, so you would still make money. So that's where they go, where they follow the subsidies rather than any sort of engineering or physical thing. Now, if people disagree about what these costs are today, then obviously they're also going to disagree about what the costs will be in the future, right? And different modelers make very different assumptions about the cost of wind and solar, and also the cost of oil and coal and gas in the future, right? So these things are fairly trivial. Let's do point number 4 first. There is a deeper issue here, and that is, how does technology actually develop? And and last week I showed the evolution of the cost of wind and solar, and they came down, right? And the question is, why? And there are some people in the literature who claim that these things just happen, that the cost of solar is falling because of progress in material science, and this is not because of climate policy. There's other people who say, well, the reason that solar and wind and batteries have fallen in cost and fallen so rapidly in cost is because of climate policy. Now, if you make the latter assumption, that if you have climate policy today, then as a result people will invest more in R&D to make the cost of alternative energy lower, then of course the implication is that if you start with climate policy, then climate policy becomes cheaper in the future because of the climate policy that you have, and as a result you end up in a very low cost scenario. And other modelers do not buy this story at all. And the reason that, even though it sounds reasonable, the reason that not everybody buys this story is the opportunity cost of R&D. So let's look at cars and engines. One way of reducing greenhouse gas emissions from the automotive sector is to have more fuel efficient cars. How do you get cars to be more fuel efficient? Actually, what you need is engineers who understand engines and can improve them. And if you say, well, if there's climate policy, then there will simply be more engineers working on engines to make them better. Is that a credible assumption? It is a credible assumption if you assume that there's lots of engineers out there who are currently driving taxis or washing dishes, and now all of a sudden there's a greater demand for engineers, and lo and behold they fill this space, right? If that is your assumption, then yeah, it's you actually get a cost reduction. And then this is fed by stories of people driving taxis in New York and meeting a very clever typically from Eastern Europe, taxi driver, right? You can also be more pessimistic and say, well, most of the people who are good at driving or who are good at engineering are engineers already. Actually, the engines that we have in cars were invented 120, 130 years ago, and have been optimized quite well, and you need very specialized knowledge. No, I mean, you can't just walk into BMW and say, you guys don't know what you're talking about and we've got to do everything differently and have a breakthrough in fuel efficiency. That's not how it works. You really need very specialist knowledge to say anything useful, let alone anything new about engines. There are, of course, very clever people who can do anything. There are geniuses who indeed, without much background in automotive engineering, can make a real contribution. But if you pull those people into improving energy efficiency, then the implication is that they're not working on other things, right? So there's also people who say, well, actually, if you start increasing the rate of technological progress in energy, then that comes at the expense of the rate of technological progress in other parts of the economy. And as I just said, energy is 2% of the economy, and yes, you can accelerate R&D there, but if at the expense, the cost of that is that you decelerate technological progress in the 98% of the economy, then of course that is a cost, right? Not a benefit. And people greatly disagree about this, how these mechanisms work and what is the strength of these mechanisms. Final point, 2 points, is what is your price elasticity? What is your substitution elasticity? Again, you can say, oh, we know that, right? No, we don't. Elasticities are actually very difficult to estimate. Elasticities are also no longer of interest to academics. It's very hard to publish a paper that estimates elasticities. So people have lost interest, and what we have is not very high quality estimates. The same is true for the capital stock. A lot of energy use is set in stone. It's machinery that you use that you don't replace immediately. It's the buildings that you have. It's where you work relative to where you live. All these things are more or less immutable in the short run. In the long run they are not. But in order to get an estimate of what it would cost to reduce emissions, you would essentially need to know what is the lifetime of a car, what is the lifetime of a piece of machinery, what is the lifetime of buildings, how quickly do people change their commuting patterns in response to price changes, and so on and so forth. And again, reasonable people can strongly disagree on how to interpret the data that there are. And for these reasons, models disagree by an order of magnitude about the costs of climate policy. One more point about policy design, and then we're going to move to the next chapter. On the left-hand side, you're looking at 5 scenarios of greenhouse gas emissions, very high at the top, and then again roughly consistent with the Paris targets at the bottom. And this is CO2 concentrations. And then for the lower scenarios, you see that there's 2 pathways of going there. One, the dotted or dashed lines, where you follow the no climate policy scenario a bit longer, and then the blue lines you deviate earlier and then relax later, but you hit the same target. Same here, but now in terms of emissions. So this is the S1000 that you see there. So there's 2 trajectories. One, you follow no climate policy and then you sharply deviate, and the other, you start deviating from the no policy path immediately, but in the end you hit the same target in concentrations at the very end. So 2 ways of getting there. One, start slow and accelerate. The other, start aggressively and then you can relax later. And the question is, which one is cheaper? And that is shown in this particular graph here for 6 alternative models. And in order to see the difference in cost, you need to compare the first to the third or the second to the fourth. And what you see is that going slow in the beginning and accelerating may be 10% cheaper. It may be 70% cheaper, depending on the model and assumptions and so on and so forth. But all these results agree that it's better to start slow. And there's 4 reasons for that. One I just said, and that is that a lot of our emissions are essentially set in stone. So it makes sense to put up an energy efficient building when it is time to build a new house anyway. It does not make a lot of sense to tear down your existing house and build a new one. That's very expensive. And actually retrofit is also fairly expensive. It's much cheaper to build an energy efficient house from scratch than to go in and change the characteristics of existing buildings. For instance, University of Sussex is, I don't know why we win prizes for being good for the environment, because we're not. And particularly in the older buildings, if you look at the windows, they're absolutely dreadful, right? Just like leak.
Isn't the most sun that, what is it?
Yeah.
Solar powered,
It's greenwashing, really. If you look at Bramber, the windows, for instance, oh my God, they're absolutely terrible. If you look at Jubilee, which is a new building, I can close the window in my office, but overnight at 5 or at 6 in the evening, the system opens my window and it's open all night, and I come in the morning, I need to close the window again. So the window is just open all night, right? So it's very badly insulated. But if you look at Bramber, it's just, the windows are just technically bad, right? They're just made of metal and can't close properly and so on and so forth. So yeah, it would make sense to do this, but it's fairly disruptive to do this, because essentially you have only a short window of time to do this, to retrofit, to knock out all the windows, replace them. It's much cheaper to build it right from scratch. So yes, you should reduce emissions, but at the time that the capital stock is renewed. When you buy a new car, when you build a new house, right? That is when you should reduce emissions. And that immediately implies that you should start slow, right? Because if you start aggressively, then essentially you're just imposing a deadweight cost on the economy. If you start with a very high carbon tax, but people cannot change their behavior because they cannot move house, then they just pay a lot of money without reducing their emissions, right? So that is the first reason why you should start slow and then accelerate. A second reason is that greenhouse gas emission reduction is cheaper in the future, because wind and solar and everything will be cheaper still in the future. So you should wait for them to start competing. It's much cheaper, and therefore starting slow and accelerating is simply cheaper. The third reason is the discount rate. That because we discount the future, incurring costs later is cheaper in net present value than incurring costs now. And the fourth reason is very similar, and that is the carbon cycle. If you have a target in the year 2100, and if you reduce your emissions in 2090, that actually has a big effect on your target. Whereas if you reduce emissions in the year 2020, because the CO2 that we put in the atmosphere is slowly degraded over time. That also implies that if we don't put CO2 in the atmosphere, then the effect of that also slowly degrades over time, right? And therefore, if you have a target for the year 2100, it's much more effective to reduce emissions near 2100 than far away from 2100. So for all these reasons, you actually want to follow the light blue path rather than start with you actually want to follow the dashed lines rather than the light blue path if your aim is to reduce emissions at the lowest possible cost. I'm actually going to make it time-wise. One more chapter and then we're going to have a break. I'm going to talk about the feasibility of very deep cuts in emissions, and I'm going to return to this particular table. And one question you may have had is, why are there so many missing values? Why is this table not full of numbers?
Negative.
No. And here we see the same results, but now graphically, and different models have different results. And if we move to more stringent targets, then more and more models do not report a result at all. So this is just the same information that we had before. And the reason that models don't show numbers is for one of three reasons. Some models say that these targets are physically impossible, that there is no emission trajectory that would actually get us to the targets, and that is because of assumptions they make about how concentrations respond to emissions. There's a few such models. There's more models that say there's no technical solution. My model cannot find energy technologies that would actually do this soon enough to get us to the Paris Agreement. That's actually the most important reason why there are so many dots in no can't do. The third reason is that some of the models say, yes, I can technically solve this, but the carbon tax I would need to impose is so high that I don't believe that this is realistic. Some of these modelers have simply refused to report the results. And we've seen that in France a couple of years ago with the yellow vest protests, right, where Macron actually tried to introduce a fairly modest carbon tax, but could not, right? He could not get it through society. And French people are greener than most. You see the same thing in the United States, where Congress still has not passed any sort of climate legislation, right, despite 20 years of trying. So yes, there are political, economic, social constraints on how fast you can go. It's of course very difficult to say where is that boundary. It's much easier to say, well, I made all these assumptions in my model and it can't do it, right? It simply can't get there. That's perhaps a more objective way of going about it. So this was the result 10 years ago or so. What has happened since, yes, it's actually running, is if models can't do it with existing technologies, can you actually introduce additional technologies to get there? So what you're looking at is trying to get to 1.5 degrees, which is the lower end of the Paris targets. Here we go again. We're looking at historical emissions, and we're looking at projected emissions that are consistent with the Paris targets. And the first thing you notice is just how steep do emissions need to go down, right? How incredibly, here we're essentially saying, well, historically we've seen it rise by 2%, 1.5% per year. Actually needs to be cut by 5-10% per year worldwide, right? That's enormously steep. Now the thing that you see emerging here are assumptions about negative carbon energy. And if it is possible to suck CO2 out of the atmosphere towards the end of the century, then your emissions need to fall steeply, but not nearly as steeply as if you don't have this technology available to you, right? And that is what the different trajectories show. Now, you may wonder, what is negative carbon energy? And last week I did not have time to talk about this. If you burn fossil fuels, then you emit CO2. We talked about that. Well, what you can do with that CO2 is, rather than vent it into the atmosphere, you can actually capture it. That's technically feasible. Transport it and store it in some safe place, either deep underwater or deep underground. There's technically no problem. Obviously we know how to capture carbon, because how would CO2 otherwise get into your beer, right? We know how to do this. We also know how to transport gas, And we have also actually we have a lot of experience in storing CO2. What you do if your oil well is getting old, your oil field is sort of slowing down and getting old, what people do is they pump CO2 into the oil field, increase the pressure so that the oil comes out. And then the CO2 is actually trapped in where used to be oil, now there's CO2 on the ground. And it's safe there and it's all fine. So we know how to technically do this. And if you believe that this is feasible at scale, this is actually one way of keeping coal and gas and oil alive, because the CO2 that otherwise would have been emitted when you burn the coal is now stored and is captured and stored, and there's no net CO2 emissions, right? Now, another thing that you can do is, instead of burning coal, you can burn wood, and you release CO2 if you do that. But when the tree grows, it of course sucks up CO2 out of the atmosphere, right? That's the carbohydrates that make up the tree. So when a tree grows, it absorbs carbon dioxide. When you then burn that tree, it releases the same amount of carbon dioxide. But of course, if you then capture and store that CO2 rather than vent it into the atmosphere, you have energy that actually on net sucks CO2 out of the atmosphere. You absorb CO2, you release CO2, but then you capture and store it. So these two cancel, and what you have is that you have negative carbon energy. And that is where the negative emissions come from. And here we see the negative emissions again. This is a different depiction. There's a range of scenarios. The central lines, the different colors have different targets, whereas this is roughly consistent with Paris, and these are less aggressive targets. And what you see is indeed, and these are global emissions of CO2, that towards the end of the century, it's not enough to reduce emissions to zero, but actually emissions need to go below zero. Right? Not if you have more lenient targets, but if you have stringent targets as agreed in Paris, then emissions will need to go negative in the long run. Slightly negative according to some models, very negative according to other models, right? This is the associated carbon tax that you will need to impose. Again, a range of model results. The price of CO2 in the year 2020 in Europe is around 100 euros per, so that makes 80, no, that makes 120 dollars per ton of CO2. So Europe is somewhere here at the moment. The rest of the world is much, much lower than that. And what you see, in order to get to these aggressive scenarios, then we should not stay at 100 in Europe. Price in the UK is slightly higher than the price in Europe. But we should actually have a price that goes up to 2,000. So CO2 has to become 200 times more 20 times more expensive than it is now by the end of the century. Oh my God, that's quite a steep price inflation, right? And of course we need to convince the rest of the world to adopt policies similar to the ones we see in Europe. So that's quite a tall order. Talked about the costs, so let's now talk about this. If we have a carbon tax on our emissions, then by implication we have a carbon subsidy on negative emissions, right? If you have to pay to emit CO2, then by implication you get paid to not submit, to absorb CO2. The fiscal implications of this are shown in this particular graph. So if we look at the dark green, we have emissions, we have the price of emissions, we multiply the two and divide it by total GDP. Here we have the fiscal implications of this scenario, right? Where you see that for most of the period you have a positive tax and positive emissions. So the Chancellor of the Exchequer is happy, right? That's a substantial income from carbon taxes, up to 2.5% in the central scenario, but maybe up to 7.5% in the more pessimistic model of GDP, right? So tax income is around a third of GDP, so 2.5 essentially means that 7.5% of government income is from carbon taxes. But then emissions turn negative, the carbon tax continues to go up, carbon tax becomes a carbon subsidy, and we are paying subsidies in the central scenario up to 4% of GDP. Unless you believe the very pessimistic model, then we're paying carbon subsidies to the tune of 17% of GDP. Now, so 4% of GDP is 12% of government expenditure. So say 10% of the government budget goes towards paying people to suck CO2 out of the atmosphere, essentially. Now, what does that mean, right? Is this politically feasible? Would you vote for a government that you will still be alive and still be allowed to vote? I'll be long dead by then. Would you vote for a government that promises to spend 4% of your income on these sort of things? Well, I don't know about your political preferences. 4% is roughly double what we pay for the army, right? This is military, more than double military expenditure, so it's a fairly substantial sum. It is much less than what we pay for healthcare, which is 8 to 10% in Europe, right? So you will say, well, it's half of what we pay for healthcare, so we can probably absorb this. But healthcare is different, because healthcare essentially pays for nurses and doctors. It pays to keep your grandma healthy, and you can see the immediate benefit of this. And even if you're not directly affected, and I hope you're not immediately in need of medical assistance, you know people who are. And you know people who are doctors and nurses and who draw an income from this. So you can sort of like see, yeah, this is something that I would support. And if you look at opinion polls, people do indeed support the government paying for healthcare. These negative carbon stuff won't be your local nurse and won't be your local doctor. And won't be the hospital that keeps your granny alive. The cheapest way of doing this is mass plantations, monoplantations of fast-growing crops. You would do it in places where the land is cheap, so far away from England, right? You would grow this in Ukraine or in Brazil, places like that. You won't see these biomass plantations in England, right? And it will be done by large corporations, large multinationals. So essentially what you're asking here is, can we on a prolonged basis give 4% of our income to multinationals for doing stuff far, far away? So for those reasons, I do not believe a word of this. Other people are more optimistic and say we can do this. Politically, I don't see how it, I mean, economically I can see how it can be done. Technically I can see how it can be done. I can't see this done politically. But that may just be my lack of imagination. So, I talked about the total cost and therefore the average cost of greenhouse gas emission reduction, but I haven't talked about the distribution of the cost. Now, economists call this incidence, which I think is a very peculiar word, not being a native speaker. When an economist says incidence of something, he or she means who pays, right? That's the incidence of a tax, is who actually pays the cost. The average cost that I discussed before, there's a knot missing here, does not tell us anything about the distribution of costs across society. And this is an important issue. Distributional issues are always important, but in this case it's particularly important because of two reasons. One, most greenhouse gas emissions are associated with the production of energy and the use of energy and the production and use of food. Those are the main sources of greenhouse gas emissions, and both are necessary goods. And that is shown in this particular graph. This is 1991 to 2007, a series of surveys, household budget surveys in the United Kingdom, and this is the Engel curve. So essentially what share of income goes towards spending on energy, total energy, electricity and gas, and what you see is that this curve the income elasticity is far less than 1, right? So if your income doubles, you spend more on energy in absolute terms, but you are not going to double your expenditure on energy. And that is shown in this graph. The implication of climate policy, essentially what you do is you make energy more expensive. If you're taxing CO2, if you're also taxing methane and nitrous, you're also going to make food more expensive. The implication for the distribution of costs across the income distribution is illustrated in this graph. This is done for the United States rather than for the United Kingdom. These are the poorest 10% of society. These are the richest 10% of society. In blue, you're looking at how much money people would spend on paying a particular carbon tax. And what you see is that, yes, everybody pays the same carbon tax, and richer people spend more money on energy, and therefore they pay more tax. But it goes from 767 up to 1800, so that is slightly more than a doubling of the carbon tax. Of course, if you compare the income of the poorest to the income of the richest, it is not a factor 2, right? It's much, much greater than that. So in pink, you're looking at what is this a share of their income, and that starts at 2.2% of income for the poorest, and then falls to 0.8% of income for the richest. So a carbon tax is regressive. It falls hardest on the poorest. Now, this used to be the conventional wisdom, and perhaps it's still the conventional wisdom. It is not necessarily true. And for that, we need to move to a more recent study than the one you see here. So this is, and there's now a handful of studies that make the opposite claim. What you're looking at, what you're looking at is again energy expenditure, but now instead of looking at income deciles, we're looking at income quintiles. So this is the poorest 20% of society, and this is the richest 20% of society. So it's the same, roughly the same data 10 years later, but slightly more crudely. And now we see what people actually spend their money on: electricity, transport fuels, and then home heating in red. Same story, right? As a share of income, the poor actually spend more than 10% of their income on energy, whereas the rich spend less than, it doesn't start at 0, right? So this is 3% it does start at 0. 0, 4, 8, 12. So this is 2% of their income, not 3%. There is another important distinction in how people get their income, and that is shown in this graph. In black, very dark blue, you're looking at the share of total income that comes from labor. In light blue, you're looking at the share of total income that comes from capital, and in red, you're looking at the total share of income that comes from government transfers. And you see a very distinct pattern here. Obviously, government transfers are much lower for the rich. For some reason, they're still positive. This is the United States, right? But another important distinction is that the capital income is much larger for the richest people in society than for the poorest people in society, for obvious reasons, right? Because you need savings, you need investments. And this actually changes the calculus, the distributional calculus. And for that we need to look at what is energy and what does it actually do. Now, electricity is pretty useless unless you have a laptop to use that electricity, or you have lights that actually can lit up. Gasoline, similarly, is pretty useless unless you have a car to put it in and drive away. So, for those reasons, energy is actually closely tied with capital, much more closely tied with capital than it is with labor. And because of that, if you increase the price of energy, you actually make capital less useful or less profitable. And the spillover of an energy tax on capital is much larger than the spillover tax of energy on labor. And you could actually argue that if you make energy more expensive, then your capital is less profitable, and the drive to automation actually slows down, and you would hire more people to make up for your lower consumption of energy in certain businesses. And therefore, these two guys, whose name will show up on the next slide, argue that a carbon tax at the end of the day is a tax on capital rather than on labor. And that would hit the rich much harder than the poor, right? So that is what is shown in this graph, and it's Larry Goulder and Mark Hofstad. I think it's Mark, but it may be Mike, but I'm pretty sure it's Mark. God, this is embarrassing. In this graph, the two effects are shown. So in the dark blue, or maybe it's black, we're looking at what actually happens to expenditure. And what you see is that the poor get hit, the rich get hit harder, but the ratio is nothing compared to the difference in income, or the ratio of incomes. But the effect of the on capital income, according to this particular model, is much larger than the effect on expenditure. And of course, because the poor don't have capital, or have very little capital, this falls primarily on the richest 20% of society. And according to this model and a couple of other models, this effect is actually numerically stronger. And if we then add in the final component, and that is the rebate that you would get, this particular picture emerges. So if the government makes greenhouse gas emissions, or the emission of greenhouse gases more expensive by levying a carbon tax, then the government has additional revenue. And in this particular model run, the assumption is that this money is redistributed to everybody by a check in the post, and everybody gets the same check. And the implication, and that is the red that you see here. So the dark blue is how much they spend extra in for their energy and their food. The red is how much they get as a check in the post, and then the light blue is how much they lose in capital income, and the rich get the same check as the poor do, so the red bar is the same, and the result is what you see here, and then the dots that you see are, so what is the total change? And what you see is that everybody in society is better off, except for the richest 20% in this particular model, in this particular policy scenario. And the implication all of a sudden is now that climate policy is progressive. It hits the rich the hardest. Now, this is a fairly new and fairly controversial result. So don't go around and saying climate policy is progressive, but the old story that climate policy is necessarily regressive, I think no longer holds. And hopefully in the next couple of years this will be tested and tested again until we know whether it is true or not. I have half an hour left for the final chapter, and I should be able to do that. And that is the chapter on negative costs. Now, ever since there's been climate policy, or the prospect of climate policy, there have been claims that it would be possible to reduce CO2 emissions and save money at the same time, that we could actually cut emissions and grow rich. Now, most of this is bogus. It's just not true. And the first mistake that people make is a confusion of market forces and policy. And last week I showed you this particular graph, and we talked at some length about energy intensity that just keeps on improving and improving and improving. Energy efficiency keeps on improving, energy intensity keeps on falling. And that's because of market forces. That, yes, if you can deliver the same product, but it uses less energy, then people will buy your stuff. Energy is a cost, and people are trying to drive that cost down. Now, there are engineers out there who think this has nothing to do with the market and everything to do with their interventions. That is a reasonable assumption to make, because it is essentially engineers who make products better. There's also a whole bunch of politicians who make the same claim, that every improvement in energy efficiency is because of their brilliant intervention. That is just a straight lie. The claim that you can reduce emissions and make money at the same time comes from the assumption that without intervention technology does not improve, which is just a nonsense assumption. The second thing that engineers get wrong is that they don't include the total cost of using new energy or new equipment. And one thing that has recently emerged is the repair of electric vehicles. So any technician, any car technician, can fix a petrol engine or a diesel engine. But in order to fix electrical cars or electric cars, you actually need specialized training. And the implication is that, yeah, as long as the car is fine, it'll run fine. But if you have a petrol car and you need it repaired, you can go to your local garage and can have it fixed at a small cost. Well, actually fairly expensive, but at a reasonable cost. But if your electric car breaks down, you face enormous costs because your local guy or girl cannot repair it, and many of the parts are actually horrendously expensive. Now, if you forget about that, if you don't include it in your model that things break and need to be repaired and what does it cost to repair, then yeah, obviously you're going to come with a lower cost. And if there's a substantial difference between the cost of repair, and which is true at the moment, and it's not just that it's more expensive to repair electric vehicles, but also you can't do it locally, that it's maybe 15 minutes or half an hour from where you live, but that you actually need to travel 2 or 4 hours to get it fixed. That actually adds to the cost, right? And if you forget these things, and typically newer technology, because we're not used to it, is more expensive to repair, right? So that is another reason why people make mistakes like this. And there's a third reason, which is the most baffling, and that is that in engineering models it is typically assumed that people can borrow money at the same rate as the government can borrow money. And it doesn't matter how often you tell them that this is just not true, that Rishi Sunak can borrow money at probably 0.25% at the moment, whereas if you go to the bank, right, they won't give you a loan because you're a poor student, and of course the government lends you money at 6%, 6.25%, right? The idea that you would have the same discount rate or the same interest rate as the government does is just a completely ridiculous assumption. It is as if the people who make this assumption have never been to the bank and asked for a mortgage and compared it to what the government pays. Because, I've said it time and time again, because energy is sort of tied up in capital, emission reduction requires an upfront investment that you then earn back later because your energy costs are lower. So you have an expenditure now, a large expenditure now, and then you have lower costs in the future. Whether or not this is a useful expenditure or a profitable expenditure depends on your discount rate. And if you assume that people can borrow money at 0.5% per year, then all of a sudden all these wonderful investments in building insulation and everything look great and profitable. But if you assume that people borrow money at 5%, then the calculus is very, very different, right? So most of these claims that you can cut emissions and make money at the same time are bogus. But there's also credible claims, or at first sight credible claims that you can do it. And that starts as follows. The model results that we've been looking at are from either optimization models or from equilibrium models. And optimization models necessarily get into an optimum, and if you assume a perfect market, then the perfect market will also deliver a social optimum, right? And of course the first welfare theorem implies that you can solve an equilibrium as an optimization problem, and you can interpret an optimization problem as an equilibrium, right? Now, if your starting point is an optimum, then anything that drives you out of that necessarily imposes a cost. The way to see this is that if you're at the top of the hill, you're in the optimum, the only way is down, right? That's the definition of being on the top of the hill. So by construction, by assumption, these models give a cost to climate policy because their starting point is some idealized world, and anything you do, you could imagine doing to this world would necessarily impose a cost, right? If on the other hand your starting point is an imperfect market, then costs can be positive or negative. If you're somewhere on the side of the hill, depending on what direction you travel, you may go up or you may go down. If at the top of the hill you can only go down, but somewhere along the hill you may go up, you may go down. These negative costs, reducing emissions while making money, come about if climate policy somehow reduces the imperfection in the market. And what people have been talking about is carbon taxes that are then used to reduce the overall distortion of the fiscal system of the economy. Now, for that we need to look at a little bit of public policy. Public economists would tell you that there's 3 rules here about how distortionary a tax is. Now, what does that mean, distortionarity of a tax? Essentially, the starting point is an economy without taxation, and what you would have then is a Pareto optimum or an equilibrium, and that would be maximizing your welfare, and that is sort of your ideal situation. Now, if the government comes along and starts levying taxes, that changes your behavior because it changed relative prices. And the people in the economy and the companies in the economy behave differently because relative prices are different, right? And then the difference in welfare between the initial economy, the ideal economy without taxation, and the economy with taxation, that relative distance is called the distortionarity of the tax, right? Now, a tax is more distortionary if the tax base is narrower, which follows immediately, right? If you want to raise £1 million in tax and you want to raise it from a few people, that is, your tax base is narrow, then you have to distort the behavior of those few more than if the tax load is spread widely over a great many people or almost all people in the economy, right? Because the amount of tax raised is the same. If you raise £1 million from 3 people in the economy or from 3 million people in the economy, you would have to distort the behavior of those 3 more than of the 3 million, right? A tax is also more distortionary if the price elasticity is higher. That is, if people respond more strongly to prices, then you distort their behavior more. You push them further away from their real behavior in the case without taxes. So those are general principles from public economics. This is a rule of thumb that the loss imposed by a tax on the economy, the amount of welfare that you reduce if you impose a tax, that deadweight loss is roughly quadratic in the level of the tax. So if you double the tax, you quadruple the cost. And this is a rule of thumb. This is not a general principle. Now, let's put these 3 things together. So what does a carbon tax do? It is a tax on energy. Everybody uses energy, right? You can't live without using energy. So the tax base is pretty broad. If you then use the tax revenue to reduce, say, labor taxes, you actually win out, because only half of the people pay a labor tax, because the other half is not in work. They may be studying, they may be retired, but they don't pay the labor tax. So the tax base of wage taxes is narrower than the tax base of energy. Right? So if you shift the tax burden from labor to energy, you actually widen the tax base and therefore reduce the distortionarity of the fiscal system. Price elasticity of energy use is actually pretty low, so you don't distort behavior that much. Price elasticity of labor taxes is actually also pretty low, so there's no real gains to be had here. Labor taxes are pretty high, so if you reduce them, you actually gain a lot in avoiding deadweight losses, whereas carbon taxes are pretty low, non-existent, so you don't lose a lot by imposing a deadweight. You don't lose a lot in deadweight if you raise such a tax, right? So for those reasons, if you shift the tax burden from labor to energy, or from labor to emissions, you're actually going to reduce the overall distortion of the fiscal distortion of the economy. And this would at least partly offset the cost of greenhouse gas emission reduction, right? Now, this is known as the double dividend. The first dividend is you raise a carbon tax, you're going to reduce greenhouse gas emissions. The second dividend is the revenue of the carbon tax is used to reduce, say, labor taxes. And that's the second dividend. There is a third effect, which according to some people is very important and according to other people is negligible, that a carbon tax is going to raise the price of energy, that is your price to you, is essentially induce inflation. And that means that you're going to reduce the real wage of people because everything has become more expensive, and you're going to reduce their returns on capital. And therefore you're going to reduce the incentive to work because you make less money working in real terms, and you're going to reduce the incentive to invest. And now this tax interaction effect partly, at least, undoes the gains of the double dividend, and there are some people who say that it actually completely offsets and changes the sign again. So those are the forces at play. Let's look at some results. And people have sort of lost interest. So these results are fairly open now. What we're looking at on the horizontal axis is greenhouse gas emission reduction, and on the vertical axis we're looking at does welfare go up, that is things get better above zero, or does welfare go down. For free alternative measures, total Higgsine equivalent, so that is essentially total consumer and producer surplus. In black, in red, we're looking at private household consumption, and in blue we're looking at total economic output, GDP, and then for a whole bunch of European countries as well as for the EU as a whole. The message here is that actually, this tax reform, shifting the burden of taxation from labor to energy for most of Europe has a positive effect, right? Regardless of how you measure positive. This particular graph does the same thing, but now looks at different ways in which you model the labor market. And the first column here is your micro labor market, where everything is perfect, right? but here there's some distortions in the labor market. Real wages are fixed, and real wages are fixed in a different way. Doesn't really matter. You still see a by and large positive effect, and actually positive here is now measured in the increase in employment. So this is positive. And then in this graph we're looking at different ways of recycling the money. What is the government actually doing with the revenue? And things look slightly more negative here. I think this story is better seen in this particular table. This is no longer the United States, this is no longer the European Union, this is the United States. It's a very old study. As you see, the proposal was to introduce a carbon tax in the year 2010, which did not happen. There's two sorts of variation here. These are 4 alternative models of the US economy. And then there are 7 ways of using the revenue. And then the numbers that you're looking at is the change in welfare. So the first scenario is that the money is sent to everybody as a check in the post, the lump sum recycling, and you see, well, this is actually has a negative effect. Because there's no stimulation, there's no change in the fiscal system, you just impose an additional tax. Actually increase the distortionarity of the tax, and then you did not use the money in any way, you just gave it back to the people. This is increase in government expenditure, and again you see overall losses. Here we're looking at a scenario where personal income taxes are reduced. The losses are slightly smaller, or a lot smaller, than in the most models, than in the lump sum scenario, but there's no dividend here, right? We're not gaining. But if you reduce corporation taxes, then we actually see some positive numbers pop up. And the same is true if you're looking at payroll taxes, particularly if you're looking at the tax that the employer pays. Now, why is this? Because in Europe we actually saw a different result. In Europe we actually saw that increasing or decreasing labor taxes had a positive effect. Now, the reason that the US is different, one reason why the US is different than the EU, is that in the EU it's households who pay the bulk of the tax, whereas in the US it's actually companies that pay the bulk of the tax. And going back to what is your starting point, and the dead weight loss is quadratic in your the level of the tax. Therefore, in the US, it would make sense to go for the most distortionary tax, which is corporation tax. The reason that the tax burdens are so very different in the EU and in the UK, in the EU and in the US, is because in the US people vote, and in the EU companies vote apparently, and the electoral system is much more responsive to people than to corporations in the US than it is in Europe. The biggest gains are found here, and that is if you increase the investment credits. Again, this is a peculiarity of the United States, and particularly in this particular year, where there simply was not enough investment in the US because they simply did not save, they consumed all their money. That has changed since the year 2000 when these models were calibrated. So what do we learn from this? It is possible to reduce emissions and make money at the same time, right? You cannot exclude that this is the case. It's within the range of possibilities. However, there's a couple of conditions that need to be met, right? First is that you're actually going to do climate policy by introducing a carbon tax. If you're going to do climate policy through tradable permits that you hand out for free, or if you're going to do climate policy through direct regulation, by setting technical standards, you don't have a carbon tax revenue to spend in a useful way, right? So that's the first condition. You actually need to do it through a carbon tax and not through some other means. The second condition is that you actually need to understand your economy. You actually need to understand your fiscal system to say, well, in Europe we need to cut wage taxes, and in the US we need to cut profit taxes, and in the US in the year 2000 we need to increase investment credits, but in the year 2020 that is no longer an issue. You actually need to understand your fiscal system and what it does to your economy, right? Now, these are all done by pretty good economists who understand these things, but of course the decisions are made by politicians, right, who do not necessarily have an intimate knowledge of how these things work. And the third condition is that even if you know how these things work, or you have smart advisors who tell you how these things work, you need to be able to withstand the political pressure of spending the money on some other priority, right? You need to be able to get your bill through Congress or through Parliament and say, we're going to do this because this is the smartest thing to do, or we're going to do this because this is the smartest thing to do. Sending everybody a check in the post is very easy to explain, right? And no doubt people will love you when you suggest that. Whereas reducing corporation taxes, that's actually hard to get applause for that, right? Because you're giving money to multinationals and their owners, right? And of course, if you're a populist politician, then spending is essentially, I can put a football stadium near you, right? Or I can build a new hospital. This is also a very popular policy, because essentially you can build big shiny things near people. So 3 conditions: you need a carbon tax, you need to understand your economy and your fiscal system, and you need to be able to withstand the forces of politics and do the right thing. So for those 3 reasons, I think that this is nice academic work. I don't really understand why anybody put any sort of credence on these things. I think it's just a bit of a pipe dream. That's all I wanted to say for today.